In general, all measurable quantities are known as physical quantities, such as mass, length, time, current, and temperature. They are also known as fundamental quantities. To measure these quantities, we use different types of devices in different situations. The smallest quantity that can be measured with a device or an instrument is called the least count of that device. Some instruments that we use to measure length are the Vernier Callipers, rulers, and meter tapes. Similarly, we measure mass with the balance, time with the stopwatch, current with the ammeter, and temperature with the thermometer. The Vernier caliper can measure up to 0.1 mm or 0.01 centimeter, while the plane scale or ruler can measure up to 1 mm or 0.1 centimeters. The devices that are used to measure mass are the common balance, digital balance, and analytical balance. The digital balance can measure up to 0.001 gram. You must have seen a digital balance in a jewelry shop. The common balance can measure mass up to 1 gram and is commonly used in grocery shops. There are devices that are used to measure time, such as the alarm clock, digital clock, and atomic clock. Atomic clocks and quartz clocks are used to measure time accurately. For example, in athletic meets and in scientific experiments. There is a new invention too, an optical atomic clock that ticks 1 million billion times every second and is at least 20 times more stable than current atomic clocks. All clocks consist of two basic mechanisms. One with the device called an oscillator, which produces periodic events moving the needle every second, and the second one for counting and displaying the time. The clocks that you have at home can measure time accurately up to 1 second. The ammeter is used to measure current. Nowadays, the multimeter is used to measure current up to 0.001 amps. Similarly, there is a device called the thermometer, which is used to measure temperature. Clinical thermometers and many electronic thermometers are usually readable to 0.1 degrees Celsius. Special instruments can give readings to 1,000th of a degree. Thus, these devices are useful to measure physical quantities accurately up to finite decimals.
Generally, an ordinary scale is used to measure the length of an object. This scale is graduated in centimeters, and each centimeter is divided into 10 millimeters. We know that the smallest measure that can be measured accurately with a device is called least count of the device. Since the least count of an ordinary scale is 1 millimeter, it is not useful to measure the length or thickness of an object with great accuracy. That is, less than 1 millimeter. In such cases, a vernier calipers is used. The vernier calipers was invented by Pierre Vernier in the year 1960. It can measure length less than 1 millimeter. Let us calculate the least count of a vernier calipers. A vernier calipers consists of two scales. One is called the main scale or ordinary scale, which is fixed. The main scale is graduated in centimeter and millimeter. The other scale, which slides along the main scale, is called the vernier scale. The vernier scale is graduated in divisions that are less than 1 millimeter. It is designed based on a principle such that n divisions on the vernier scale coincide with n-1 divisions on the main scale. Thus, the least count of the vernier calipers is equal to the difference between the values of one division on the main scale and one division on the vernier scale. That is, least count is equal to 1 MSD minus 1 VSD. The least count of vernier calipers is known as the vernier constant. Let the value of one main scale division be S and the value of one vernier scale division be V. From the principle of the vernier calipers, N into V is equal to n-1 into S. On simplifying, the equation can be written as S minus V is equal to S by N. Since the difference between one main scale division and one vernier scale division is equal to the least count of the vernier calipers, the least count can be written as S minus V, which is equal to S by N. This is equal to the value of one main scale division by the number of vernier scale divisions. Generally, in a standard vernier calipers, 10 vernier scale divisions coincide with 9 main scale divisions. Since the length of each main scale division is 1 millimeter, 10 divisions on the vernier scale are equal to 9 millimeter. Therefore, the value of one vernier scale division is equal to 9 by 10 millimeter, which is equal to 0.9 millimeter. Thus, the least count is equal to 1 millimeter minus 0.9 millimeter, which is equal to 0.1 millimeter. In another way, the least count is equal to one main scale division by the number of vernier scale divisions, which is also equal to 0.1 millimeter. Let us now take a look at the vernier calipers. A vernier calipers consists of a long, thin metallic strip called the main scale. The main scale is graduated in centimeter and millimeter. Each division on the main scale is equal to 1 millimeter. This metallic strip is provided with a jaw, J1, on the lower side at its end, which is called the fixed jaw. A metallic frame on the right side of the fixed jaw slides over the main scale, called the vernier scale. On the bottom edge of this frame is a graduated scale. It usually consists of 10 equal divisions that coincide with 9 main scale divisions. The value of each vernier scale division is equal to 0.9 millimeter. This vernier scale is provided with a jaw, J2, on the lower side, which can move with the vernier scale. This jaw is called the movable jaw. The vernier calipers is also provided with 2 more jaws, J3 and J4, on the upper side. J3 is attached to the main scale and J4 to the vernier scale. A screw S is attached to the main scale. It is used to fix the vernier scale at any position on the main scale. The jaws on the lower side, J1 and J2, are called the external jaws. These jaws can hold the object firmly and help to measure the length of a rod, diameter of a sphere, and external diameter of a cylinder, etc. The jaws on the upper side, J3 and J4, are called the internal jaws and are used to measure the internal diameter of a hollow cylinder. A thin and long strip T is attached to the vernier scale at the back of the main scale. This strip is called the tail and is used to measure the depth of hollow cylinders and small beakers. Further, the main scale and the vernier scale are also graduated in inches, which helps in measuring dimensions in inches. Let us now see how the length of an object is measured using the vernier calipers. The object is held by the external jaws of the object, such that the readings on the main scale and the vernier scale are as shown in the figure. From the figure, it is clear that the length of the object is AB. AB can be written as the sum of AC and CB, where AC is the main scale reading, MSR, and CB is the fractional reading, which can be determined with the help of the vernier scale. The fractional reading CB is equal to CD minus BD. Note down the number of the division on the vernier scale that exactly coincides with the definite main scale division. This division is called the vernier coinciding division, VCD. Let this be N. From the figure, CD is equal to N main scale divisions. BD is equal to N vernier scale divisions. Then, CB is equal to N main scale divisions minus N vernier scale divisions. On taking N common, CB can be written as N into 1 main scale division minus 1 vernier scale division. You know that the difference between 1 main scale division and 1 vernier scale division is equal to the least count. Therefore, CB can be written as N into least count. But N is the vernier coinciding division. Therefore, the fractional reading, CB, is equal to vernier coinciding division into least count. The length of the object, AB, is equal to main scale reading plus fractional reading, which is equal to main scale reading plus vernier coinciding division into least count. Before measuring the length of an object using the vernier calipers, you need to check whether the instrument is error-free. Bring the two external jaws, J1 and J2, in contact. If the 0 on the main scale coincides with the 0 on the vernier scale, then the vernier calipers is free from error. In this condition, the tail of the vernier calipers just touches the end of the main scale strip. If the 0 on the main scale does not coincide with the 0 on the vernier scale, then the vernier calipers is said to have zero error. There are two types of zero errors. They are positive zero error and negative zero error. With the two external jaws in contact, if the 0 of the vernier scale is on the right side of the 0 of the main scale, then the zero error is said to be positive. The error is equal to the distance between the main scale 0 and the vernier scale 0. The positive zero error is equal to the vernier coinciding division into least count. The correction for a positive zero error is equal to minus of positive zero error. To get the correct reading, the correction should be added to the observed reading. Thus, corrected reading is equal to observed reading plus positive zero correction. For example, when the two external jaws are brought in contact, if 0 of vernier scale is on the right side of the 0 of the main scale and fourth division on the vernier scale coincides with one of the main scale divisions, and least count of the vernier calipers is 0.1 mm. In this case, the positive zero error is equal to 4 into 0.1 mm, which is equal to 0.4 mm. Thus, the positive zero correction will be minus 0.4 mm. When the two external jaws are in contact, if the 0 of the vernier scale is on the left side of the 0 of the main scale, then the zero error is said to be negative. The error is equal to the distance between the main scale 0 and the vernier scale 0. The negative zero error is equal to minus of total number of divisions on the vernier scale minus vernier coinciding division into least count. The correction for a negative zero error is minus of negative zero error. To get the correct reading, the correction should be added to the observed reading. Thus, the corrected reading is equal to observed reading plus negative zero correction. For example, when the two external jaws are kept in contact, the 0 of the vernier scale is on the left side of the 0 of the main scale, and the 7th division on the vernier scale coincides with one of the main scale. The number of divisions on the vernier scale is 10, and the least count of the vernier calipers is 0.1 mm. The negative zero error is equal to minus of 10 minus 7 into 0.1 mm, which is equal to minus 0.3 mm. Then, the positive zero correction is equal to minus of minus 0.3 mm, which is equal to 0.3 mm. Let us now see how to measure the length of a cylindrical rod. First, find the least count, LC, of the vernier calipers. Bring the two external jaws in contact and check the position of 0 on the main scale and the vernier scale to see if there is any error. If there is any error, then note it down and calculate the zero correction. The movable jaw, J2, is moved and the cylindrical rod whose length is to be measured is placed between the two external jaws. Now the vernier scale is fixed by tightening the screw S. Note the reading on the main scale just before the 0 of the vernier scale, which gives the main scale reading MSR in centimeter. Note down the division on the vernier scale that coincides with any one of the divisions on the main scale. This gives the vernier coinciding division VCD. Multiply the vernier coinciding division with the least count and convert it into centimeter. The observed reading is equal to main scale reading plus vernier coinciding division into least count. The corrected reading is equal to observed reading plus zero correction. Repeat the procedure by placing the object in different positions along its length. The readings are tabulated as shown. The average of the corrected readings gives the length of the object accurately. To find the inner diameter of a hollow cylinder, fix the cylinder to the internal jaws and follow the same procedure. Similarly, to find the depth of a hollow cylinder or a small beaker, place the tail of the vernier calipers along its depth and follow the same procedure. You know that you can use an ordinary scale to measure up to 1 millimeter accurately. You also know that you can use the vernier calipers to measure up to 0.1 millimeter accurately. The least count of the vernier calipers is 0.1 millimeter. Therefore, you cannot use it to measure any dimension less than 0.1 millimeter accurately. A screw gauge is used in such cases. It is used to measure up to 0.01 millimeter with greater accuracy. Thus, it can be used to measure the thickness of thin objects like wires, glass sheets, and so on. The screw gauge works on the principle of a screw in a nut. The screw gauge consists of a U-shaped metallic frame. One end of this U-frame has a fixed flat shaft called the stud or anvil. It forms the fixed jaw of the screw gauge. The other end of the U-frame has a long hollow cylinder with fine threads inside. This serves as the nut. This cylinder is called the sleeve cylinder. On the outer surface of the sleeve cylinder, a line parallel to the axis of the cylinder is engraved. This line is called the index line or base line. The index line is graduated in millimeters or half millimeters. This is called the pitch scale or main scale. There is a screw with a flat tip and threads on its outer side, identical to the threads cut inside the sleeve cylinder. This is called the spindle. The spindle moves inside the sleeve cylinder. The flat tip of the spindle is nothing but a shaft which forms the movable jaw of the screw gauge. The other end of the spindle is connected to a milled head. To the milled head, one end of another hollow cylinder is connected. This hollow cylinder is called the barrel. The other end of the barrel is tapered and graduations are made. There are either 50 or 100 equal divisions on it. This is called the head scale, circular scale, or thimble. The end of the screw is connected to a ratchet by means of a spring. When the flat tip of the screw comes in contact with the stud, the ratchet becomes free and makes a rattling sound. Thus, the tip of the screw cannot be pushed further towards the stud. The screw gauge is also provided with a lock nut, which holds the scales at a particular position to prevent errors. Let us now measure the diameter of a metal wire. Before making a measurement, you should first determine the pitch of the screw, the least count, and zero error of the instrument. When the head of the screw is rotated, the tip of the screw moves either forward or backward. The distance traveled by the tip of the screw in one complete rotation of its head is called the pitch of the screw. This distance is equal to the separation between two adjacent threads on the screw and parallel to its axis. To find the pitch of the screw, rotate the head of the screw till the zero of the head scale coincides with any one of the divisions on the pitch scale. Let us say the head scale is at 5 millimeter. Then turn the head scale, which has 100 divisions on it, by a certain number of rotations, say 5. After 5 rotations, the zero of the head scale is at 10 millimeter on the pitch scale. Note the distance traveled by the screw in 5 rotations. Here, it is equal to 5 millimeter. Then the pitch of the screw is equal to the distance traveled by the screw on the pitch scale divided by the number of rotations made by the head scale. Therefore, the pitch of the screw is equal to 5 mm by 5, which is equal to 1 mm. Using the pitch of the screw, let us calculate the least count of the screw gauge. You know that least count is the smallest measure that can be made accurately by an instrument. When the head scale is rotated such that only one division on the head scale crosses the index line, the distance travelled by the head scale along the index line is called the least count. In another way, the least count is equal to the pitch of the screw divided by the number of head scale divisions. As the pitch of the screw is 1 mm and the number of head scale divisions are 100, the least count of the screw gauge is 1 mm by 100, which is equal to 0.01 mm. Before making a measurement, you must also check if the screw gauge has any zero error. Rotate the head scale such that the tip of the screw is in contact with the stud. If the zero of the head scale coincides with the index line of the pitch scale and the head scale is exactly on the zero of the pitch scale, then the screw gauge has no zero error. However, if the zero of the head scale does not coincide with the index line, then the screw gauge is said to have zero error. There are two types of zero errors. They are positive zero error and negative zero error. When the tip of the screw is in contact with the stud, if the zero of the head scale is below the index line of the pitch scale, then the error is said to be positive zero error. If n is the coinciding division of the head scale with the index line of the pitch scale, then the positive zero error is equal to n into least count. Then the positive zero correction is minus of positive zero error. That is, the correction for positive zero error is negative. For example, if the sixth division on the head scale coincides with the index line of the pitch scale and the least count of the screw gauge is 0.01 mm, then the positive zero error is equal to 6 into 0.01 mm, which is equal to 0.06 mm. Then, the positive zero correction is minus of positive zero error, which is equal to minus 0.06 mm. When the tip of the screw is in contact with the stud, if the zero of the head scale is above the index line of the pitch scale, then the error is said to be negative zero error. If n is the coinciding division of the head scale with the index line of the pitch scale, then the negative zero error is equal to minus of number of divisions on the head scale minus n into least count. Then the negative zero correction is minus of negative zero error. That is, the correction for negative zero error is positive. For example, if the 96th division of the head scale coincides with the index line of the pitch scale, the total number of divisions on the head scale is 100 and the least count of the screw gauge is 0.01 mm. Then, the negative zero error is equal to minus of 100 minus 96 into 0.01 mm, which is equal to minus 0.04 mm. Then, the negative zero correction is equal to minus of minus 0.04 mm, which is equal to 0.04 mm. Now let us measure the diameter of a wire with a screw gauge. After calculating the pitch of the screw, least count and zero error, if any, rotate the head scale anti-clockwise so that the shafts open. Place the wire between the stud and the tip of the screw. Rotate the ratchet clockwise so as to hold the wire tightly between the stud and the tip of the screw. Note the reading on the index line just before the head scale. This is the pitch scale reading or main scale reading. Note the reading on the head scale that coincides with the index line of the pitch scale. This reading is called head scale reading or circular scale reading. The observed diameter of the wire is equal to pitch scale reading plus head scale reading into least count. To get the correct diameter of the wire, the positive zero correction or the negative zero correction of the device should be added to the observed diameter of the wire. Repeat the procedure by taking readings at 4 or 5 different parts of the wire and tabulate the readings. The average of the corrected diameters gives the actual diameter of the wire. Sometimes, due to wear and tear of the threads of the screw, the tip does not reverse immediately on rotating the head scale back. This is called backlash. This causes an error in the observation and is called backlash error. To avoid backlash error, the screw should be rotated in one direction only. Seen different types of substances such as solids, liquids, and gases. The space occupied by a substance is called its volume, which is denoted by V. The unit for volume in the MKS and SI systems is meter cube or cubic meter. 1 meter cube is defined as the volume of a cube of side 1 meter each. In the CGS system, the unit for volume is centimeter cube or cubic centimeter. 1 centimeter cube is defined as the volume of a cube of side 1 centimeter each. 1 meter cube is equal to 10 to the power 6 centimeter cube. A gas does not have definite volume. It occupies the total volume of the container in which it is filled. However, liquids and solids have definite volumes that can be measured. Let's see how the volume of a liquid and a solid is measured. Solids have a definite shape and size, but liquids do not have any particular shape. They take the shape of the container into which they are poured. The volume of liquids is measured in liters and milliliters. 1 liter is equal to 1000 milliliters. 1 liter is defined as the volume of 1 kilogram of pure water at 4 degrees Celsius and normal atmospheric pressure. Although the liter is not an SI unit, it is accepted for use with the SI. When we take a liquid in narrow tube, it forms a curved surface. The curved surface is called meniscus. The surface of all liquids, except mercury, curves downwards. This is called concave meniscus. On the other hand, the surface of mercury curves upwards, which is called convex meniscus. Hence, while measuring the volume of liquids in narrow tubes, take the reading at the lower meniscus for all the liquids except mercury and at the upper meniscus for mercury. The reading should be taken without parallax error. To avoid parallax error, place your eye at the level of the lower meniscus for all the liquids except mercury, and at the level of the upper meniscus for mercury. The apparatus used to measure the volume of a liquid are the measuring cylinder, measuring flask, pipette, burette, etc. We will now study these apparatus in detail. The measuring cylinder is a glass cylinder graduated into milliliters and cubic centimeters. Pour the given liquid carefully into the measuring cylinder so that no air bubbles are trapped inside. Note down the reading against the level of the liquid without any parallax error. This reading gives the volume of the given liquid. The graduations on the measuring cylinder indicate the volume of the liquid. Let us now look at the measuring flask. There are two types of measuring flasks, round-bottomed and flat-bottomed. The measuring flask consists of a long, narrow neck provided with a stopper. A graduation mark is etched on the neck. If the measuring flask is filled with a liquid up to the graduation mark, it contains a fixed volume which is indicated over the flask. Measuring flasks are available in different capacities like 50 milliliters, 100 milliliters, 250 milliliters, and so on. Another measuring device is the pipette. The pipette is used to measure a definite volume of liquid. It is generally used to transfer a definite quantity of liquid from one vessel to another. It consists of a cylindrical glass bulb with narrow glass tubes above and below it. The lower end of the glass tube is tapered. A graduation mark is etched on the stem. The liquid filled in the pipette up to this mark represents its capacity, which is indicated over the glass bulb. To measure a definite volume of a given liquid, immerse the narrow end of the pipette into the given liquid. Hold the stem of the glass tube and suck the liquid till its level rises a little above the mark on the glass stem. Be careful not to suck the liquid into your mouth. Now cover the mouth of the pipette with your finger. Hold the pipette vertically and release the finger slowly till the level of the liquid comes to the mark on the glass stem. Then close the finger and introduce the pipette into a beaker and release the finger. The liquid in the pipette runs down into the beaker, but a little of it remains in the narrow end. This can be collected by tapping the tip of the pipette against the beaker. By using a pipette, we can collect only a fixed amount of liquid. We cannot collect the fractions of the volume displayed on the bulb. To collect fractions of a certain volume, we use another device called the burette. The burette is a long cylindrical tube with a nozzle at one end. The cylindrical tube is graduated in milliliters or cubic centimeters. The volume of the liquid to be collected can be controlled with the help of a tap fixed at the nozzle. The burette is clamped in a vertical position to a stand and is filled with the liquid. Open the tap and allow a little liquid to run down, and then close it to let the air in the nozzle run out. To collect some volume of the liquid in a beaker, place the beaker below the nozzle. Note the original level of the liquid in the burette. Open the tap and transfer some liquid into the beaker and then close the tap. Note the level of the liquid in the burette again. The difference between the readings gives the volume of the liquid transferred into the beaker. There are many other devices to take fixed volume of liquids. They are the conical flask, measuring vessel, etc. Coming to solids, they are regular or irregular in shape. If a given solid substance is regular in shape, its volume can be found by measuring its dimensions and substituting the values in the formula for volume of the corresponding shape. Let us see the formulae for the volume of some regular shaped objects. The volume of a cuboid of length L, breadth B, and height h is the product of length, breadth, and height. That is, V is equal to L into B into h. If the length, breadth, and height are equal, a cube is formed. Let A be the length of each side of the cube. Then, its volume V is equal to A into A into A, or A cube. The volume of a sphere of radius r is 4 by 3 into pi r cube. The volume of a cylinder of height h and radius of base r is pi into r square h. The volume of a cone of height h and radius of base r is 1 by 3 into pi r square h. Thus, by using these formulae, we can find the volume of regular shaped solids. If a solid object has an irregular shape, a stone, for example, then its volume can be measured in two ways. One is by using a measuring cylinder, and the other one is by using an overflow jar. Let us see how to measure the volume of an irregular object with the measuring cylinder. Take a measuring cylinder and fill it with water up to a certain level. Note down the volume of water by placing the eye at the level of lower meniscus. Let this volume be V1. Now tie the given irregular solid object to a thin long thread. Lower the solid object slowly into the cylinder so that the object is completely immersed in the water. The level of the water in the measuring cylinder rises. Note down the volume of water again. Let this volume be V2. Thus, the volume of the irregular object is equal to the difference between V2 and V1. If the given irregular object is lighter than water, then a heavy solid insoluble in water, such as a piece of stone or metal, is used along with the given object. This heavy solid is called a sinker. Subtract the volume of the sinker from the increase in the volume of water to get the volume of the lighter object alone. Let us now measure the volume with an overflow jar. An overflow jar consists of a vessel with an outlet or spout. Fill the overflow jar with water till the level of the water reaches the spout. Take a measuring cylinder and place it below the spout of the overflow jar. Now, tie the given irregular object to a thin long thread. Gently lower the irregular object into the overflow jar. The irregular object displaces some water from the overflow jar into the measuring cylinder through the spout. The volume of the water displaced is the volume of the irregular object. This method is called displacement method. If the solid is soluble in water, then use a liquid in which the solid is insoluble. Here is a conversion table for the units of volume.